Hello everyone, this is video 3.1 and 3.2. We're going to do these two sections together, and so all the material from the two will be combined. I'll let you know when we switch over to section 3.2. Section 3.2 is on the part about commutative and associative properties. So when we get to that point, I'll let you know. So in case you want to cross-reference the video with the book, you'll sort of know where to look. But we'll start in 3.1, and then I'll let you know when we get to 3.2. So let's get started. So, a lot of terms to define, a lot of terms to define. And most of these terms you probably already know. One or two of them you may not have heard for quite some time. Obviously, you need to know all these terms. We got to make sure that we call these things by the right names. So, we'll go through these terms real quick. So, the sum is the answer we get from an addition problem. And so, when we perform an addition problem, with the answer that we get, call the sum. Pretty straightforward. The things that we add together, we can call them a bunch of different things. Now, terms is kind of a generic name that we can use. Um, More specific to addition is if we call them add-ins. It's also not a term that you hear very often, and summands you probably hear even less than that. So you can get away with calling them terms. I would say from time to time, try to remember to use add-ins. I mean, it is the operation specific term. So, when you can, throw that out there. But if you say terms majority of the times, most students will understand what you're talking about. They'll pick up on that, and you're not too far wrong. This is these are our terms for addition. For subtraction, we have a couple of more, and we'll talk about the reasoning behind this a little bit more when we get to commutativity. The answer that we get to a subtraction problem we call the difference. The things that we're subtracting, generically we could refer to as the terms. But because the order matters, because 5 minus 2 is not the same as 2 minus 5, calling them terms can be a little misleading and a little confusing. I'm doing a subtraction problem and the terms are 2 and 5. Doesn't really let me know which problem I'm doing. So we can refer to them as terms in certain contexts where we can recognize it's not going to be too confusing for the students. But generally, you'll want to refer to them as minuend and subtrahend. Please try to resist the urge, fight the urge to just say first number, second number. In the same way that when you're doing fractions, you have to kind of resist the temptation to just say top number, bottom number. I mean, these have names. We can't expect students to use the proper terminology if we never use the proper terminology. So make sure that you know minuend and subtrahend. Minuend always makes me think of minuet, which makes me kind of happy. Subtrahend just makes me think of subtrahend. But make sure you know these two terms. You will see these terms again, so make sure you know those terms. So let's talk very briefly about what is addition. What do we really mean by addition? And for a lot of people, when they think of addition, they think of an addition table. They think of a big chart that you had to memorize at some point, and that's a form of addition. Without getting too much into the educational aspect of it, that is a memorization, that is a knowledge domain, to use the Bloom terminology. It's a very low order of knowledge. We can't say that it's not knowledge because it's certainly knowledge, but we could argue that it's not understanding. A student can just sort of parrot that 5 plus 5 is 10 without having really any understanding of what that means. So let's look at a problem like 3 plus 4 equals 7. And so what this means is that I have a set of 3 objects. I have a set of 4 objects. So here's my 3, here's my 4, and then this addition sign means that I'm going to combine these two sets together. They go to form one set. And so addition really means the combination of sets. So addition is the combination of sets, or really, if we want to be really particular about it, we could say the combination of the cardinality of the sets. because what we're going to do is we're going to combine those sets together, and then we're going to take the cardinality of that newly formed set. So we're really thinking about not just the sets. Um, so we could put and their cardinalities. So we take the set of three, we take the set of four, we put them together, and we make the set of seven. Now, on top of that, we could layer on what we talked about in chapter one with ideas of grouping and regrouping. And if we were to add 6 plus 8, then we have 14. And so we would have 10 of those little units. We could group those together into a long, et cetera, et cetera, et cetera. But just focusing on the idea of what do we mean by addition, what it really means is that we're combining sets together. Now, this is a much more complicated question. I think most people have a pretty good intuitive sense of what addition means, but what we mean by subtraction is a little bit more complicated because for a lot of people, they think of subtraction simply as the addition of a negative. So if I were to have the problem 7 minus 4, a lot of people are going to think of this as 7 plus negative 4. This is bad for a couple of different reasons. Number one is it introduces negative numbers where we just simply don't need them. And we're going to get into uh, some some problems later on in section 3.5 where it's going to be a whole lot easier to keep this as subtraction than it is going to be to make this adding a negative. The other thing that's crucial about this and that this process sort of confuses is it makes subtraction almost irrelevant. It makes it sort of just an extension of addition. Um, Changing every subtraction problem to an addition problem doesn't build any concept or fluency around what subtraction actually means. It just takes everything and converts it back into addition. And subtraction is its own operation. So if we know that addition is the combination of sets, then subtraction should be the removal of sets. And so what a lot of people will do with this problem, and if you want to take a second to think about 1, 2, 3, 4, 5, 6, 7. So think about how you would model this problem. And what a lot of people do is they'll make a set of 7, and then they'll make a set of 4, and maybe they'll make it in a different color like this. And then they will cross these out and get positive 3. And really what you've done is you've done 7 plus negative 4. You've done 7 up here, and you've added in negative 4. And then you've done this cancellation of the positives and the negatives, and you've gotten your answer. This is not the model for subtraction because you've added two sets together. You've taken a set of 7 and a set of 4, which is sort of implicitly negative, and then you've combined those together and done cancellation, which is essentially adding a negative number. This is not subtraction. It's just simply not. So this is a viable model if we're talking about 7 plus negative 4. But if we're talking about 7 minus 4, 3, 4, 5, 6, 7, we're going to start with our set of 7. And subtraction means the removal of a set. So we're going to remove that set of 4, and then we're going to see how much is left. There's my difference right there of 3. So if you have a hard time sort of thinking about what subtraction is, other than combining two sets together, that's a pretty good indicator to yourself that maybe you're thinking about subtraction needs a little bit of support as well. And if we think about things in a certain way, then we're going to sort of pass that on. It's not a bad thing. It's not a judgment on you if you think of subtraction only as addition. It just means that there's a little bit of a gap in your thinking about this level of mathematics that you need to fill in before we start teaching it. It's a really common thing. It's how a lot of us were taught, and so it's a lot. It's a lot of how we probably would have seen this in school to be thinking about this if we saw it as a model at all, to just sort of like cancel these things out. But it's important that we think about subtraction as its own operation. This brings us to this idea of fact family problems. And so we looked at a set model in the previous example. We can look at this as a strip model now. So I'm going to draw two strips like this. And then the top one, I'm going to tell you is 7. And then down here, this is 4, and then this is 3. And so what you would do with a problem like this is ask your students, so what problem, what mathematical problem, or what mathematical statement can we see from this diagram? And so one of the statements that we can see is 4 plus 3 equals 7. So we can see that this 4 along the bottom and this 3 along the bottom are the same length. So we can see that they start and stop in the same place. So they're the same length. They have the same measurement. So 4 plus 3 equals 7. Now, we would also take 3 plus 4 equals 7 as a separate answer because we haven't done commutativity yet. And so there may be some students who will recognize that 4 plus 3 and 3 plus 4 are the same thing, but we haven't really formalized that yet, so I'll take those as two separate answers. We also have 7 minus 4 equals 3. And so from this 7, if I take off this 4, I have 3 left. And then this 7 minus 3 equals 4. So you can also see the other reason for keeping these two addition problems is it keeps this nice symmetry, 2 addition and 2 subtraction. So this diagram gives us this family of problems, or this family of statements that we can make mathematically. And so from each one of these diagrams, we should be able to get at most 4. Now, if we have 3 plus 3 equals 6, we're only going to get 2 problems from that. We're only going to get 3 plus 3 equals 6, and 6 minus 3 equals 3. We're not going to count 6 minus 3 equals 3 twice as 2 separate problems. That's just being kind of silly. So as long as if the numbers are distinct, we'll get 4 problems. So this is a nice way, a nice open-ended way of posing a problem to students to see their fluency in making the connection between this model and addition and subtraction as operations. It's a really common problem type that you'll see in a lot of books and in a lot of classrooms. And I really like it because, like I said, it's so open-ended. It's a lot better than just saying what's 3 plus 4 and having half the class say 7 and then taking that as assessment. We can also talk about addition and subtraction as comparison problems. And so we can look at a problem like Alice has 14 candies and Bob has 9 candies. Who has more? Which is an inequality problem. And then how many more do they have? So whichever person has more, how many more candies do they have? And so this is a lot like a fact family problem. So we'll model this with a number line. So here's Alice, and she has 14 candies. And here's Bob, hi Bob, and he has 9 candies. And so we can see that Alice has more, because 14 is greater than 9. But then how many more? And so we would need to figure out what this is in here. And we can do this a couple different ways. We could do this as 9 plus what equals 14. We could also do it as 14 minus what equals 9. And so you can see that really what we have here is a fact family type problem, because we could also do this as something plus 9 equals 14. We could also do this as 14 minus 9 equals something. So all 4 of these interpretations are absolutely fair and reasonable for this problem, but it's done in a word problem context. So now moving into section 3.2, and I'll put that over in the corner here. We're now starting. So section 3.2, we have this property called the commutative property, which you've seen before. Whether or not you remember it or have done an awful lot with it, you've definitely seen it. You need to know this property, and you need to know the name of this property. You need to recognize this property when you see it. And it says that a plus b equals b plus a. And so our 3 plus 4 that we saw earlier that equaled 7 is going to be the same as my 4 plus 3, which both equal 7. Now, it's really important to note that the commutative property does not apply to subtraction. So obviously, 3 minus 4 is not the same as 4 minus 3. You will get students that will point out when you say this, but 3 minus 3 does equal 3 minus 3. So why doesn't that mean that subtraction is commutative? And the answer is this has to work for all cases. So for addition, this works. Doesn't matter what two numbers I pick, I can add them in either order and they work. They work for all cases. For subtraction, they only work for very specific cases. They only work in the case where the two numbers are the same. And so the commutative property, when you see this, sometimes it'll be written something like this, like for all A, B, or it'll say for all A and B. It'll say that for all A, B. And a lot of times students will just focus on this part of it and not focus on the restriction. Or to be honest, a lot of teachers will just focus on this part and not focus on the restriction. But the restriction is important because it lets us know that there's going to be times where it works in some cases. We're not interested in some cases. We're interested in all cases. Now, there are properties that are some case, not all case, but these properties that we're looking at right now, they have to work for all cases. So that's a commutative property. We can compare this to the associative property, which again is an addition property. And this says that if I take three numbers, that I can add them in some order. Either I could add the B and the C first or the A and the B first. Now, this may seem like a silly, almost like pointless property, but the reason is that addition and subtraction are what we call binary operations. And that doesn't mean that we're adding binary numbers. What binary in this case means is that really I can only add two things at a time. And so even if you were to take like a list of numbers, if we were to do 17 plus 8 plus 3, you might argue, well, we're adding all three of these at the same time. And my argument would be, well, no, we're really not. We're thinking about this really in terms of two numbers at one time. So if you were to go through and add these together, you would either do 17 plus 8 is 25. And so you've done two numbers together, plus 3 is 28. You've done 25 and 3 together. Or you might do the ones places together. You might do it 17, 8, and 3 like this. So 7 and 8 is 15. So again, we're doing two numbers at a time. Plus 3 is 18. That's an 8, carry the 1. And now we're adding 1 plus 1 makes 2. So even though there may be more than two numbers involved in the problem at a time, we're really only working with two numbers at a time. And so that's what this tells us, is that which two I take doesn't make a difference. I could have added this instead of going 7 plus 8 and then plus 3, I could add going up and say 3 plus 8 is 11, plus 7 is 18. I get the same 18. So it's going to work either way. So that's what the associative property tells us. Again, it may seem silly, it may seem pointless. There are very good reasons for it, not all of which we're going to explore in this class, and not all of which you're probably going to explore with your students. But as far as making math as a system work, it's one of those sort of rules that we have to have in there to make sense of some things that do happen in mathematics. So let's look at a problem where we sort of combine these two things together. And so let's go back to that 17 plus 8 plus 3 problem. And so one of the things that you might notice is that the 17 and the 3 make a 20. And anytime that we can work with what we call compatible numbers, so anytime we can work with compatible numbers, it's going to make things a whole lot easier, not even for us, but for students. So this making a 20 sort of lets us not have to worry about the ones place, because the ones place is a 0. So how do we add the 17 and the 3? Well, you might think, well, we just add the 17 and the 3. But if we really want to play by the rules, we have to use the two properties that we've just seen. So the first thing we can do is use the associative property on the 8 and the 3. And so we're using the associative property. Always be careful how you abbreviate associative. Now I'm going to use the commutative property. I'm going to use the commutative property to switch these around. And now I'm going to use the associative property one more time. You could say this is by definition of grouping, but I would just call it associative. Either way would work. So now I'm going to use the associative property to move these parentheses over here. And now I have my compatible numbers together. 20 plus 8 equals my 28. I'm not suggesting that we go through this process every single time, but it is worth going through this process at least a couple of times so we see how these properties work and we can see why they are important. I also want to point out that we could use this idea in solving problems like 17 plus 11. And so students might look at this and struggle with what's going on here. So we could use the idea of compatible numbers to make the problem a little bit easier and say, well, okay, well, how many further away do we need to go to get to a multiple of 10? And so this 17, we just need 3. So we could break that 11 into 3 and 8. And so now we have effectively this problem. So this is a process that you'll see a lot of students working with, especially if they are working with, say, number lines like this. And so you have to add 11. And so you'll see plus 3 goes to 20, but now we have to make the full 11. So now plus another 8 makes 28 for our answer. So this is an idea that uses compatible numbers, but is also using associativity and commutativity because we're moving these things around into an order that sort of benefits us. So the last thing is a checkpoint problem. I want you to think about two different ways, two different models, not necessarily that we've talked about in these slides. So go back and think about some of the models and some of the ideas we've talked about in chapter 1, or maybe even chapter 2, of how we could explain to students how to solve 17 plus 29. I want you to avoid the standard algorithm, right? So we're not going to do 7 plus 9 is 16, put a 6, carry the 1, just without, any sort of meaning to it. So I know that you can find the answer. I know you know the answer is 46. That's not the issue. I want you to think about how you would explain the process of how to get to the 46 two different ways. So I'll leave that as your checkpoint problem. If you have any questions, please, by all means, bring them to class, email me, let me know, and we'll get them answered. All right, thanks.